Okay, I guess it's about time to start. So welcome back to class. I have a handful of announcements to make. So let me march through those before we get to the class material. The first thing is I'd like to mention a couple things on Blackboard. So I'm going to try to share my screen here. And let's see. Okay, this is week 12 of the course. And incidentally, my father's 90th birthday. So he's made it a good long ways. I don't know what it feels like to get old enough that you see your children getting kind of old. So, but he's still going. What I wanted to mention to you, there's a folder here called Octave/MATLAB demonstration files. There's some instructions on how to use these. And what these will do is if you, I'm not sure if we can view this. Probably it wants to download if I click on it. Oh, let's try a browser window. See if it works. Sort of, it works. You see, this is a very short text file, and that is not all that helpful by itself. So let's see. You're seeing that, I hope. But these are files with code that will execute in MATLAB or in Octave. And you can install Octave for free on your own machine, or you can get it online. And actually, I think I got to change windows here. I am I have a version of Octave installed on this workstation. Don't mention it to tech support. I'm sure they wouldn't approve. But you can do it because there's a portable version that doesn't change registry entries or any of that sort of thing. It just sits there as an executable file and runs. So if you want to run it on your own machine and you don't want to install something only to have it leave bits and pieces around, that is an option. You can do a search for the Octave portable version, or you can get it online. And at this point, let me see if I can get this working a little bit more smoothly here. Okay, I think you all can see my screen now. If not, do let me know. So yes, I've logged on to this website already. And it will give you the option, this is Octave Online. I don't care if you use this or any other way of using MATLAB or Octave. It's all the same to me. And the output should all be very, very similar. I don't know if there would be any detectable difference or not. You do have the option at Octave Online of creating an account. And all I had to do for that was I gave them an email address. And then they send me a link and I double click that in my email and pop into this, or they give you a passcode you type in. So if you create an account, you get this interface. And what you can see in this interface is, they're helping so much it's hurting, is over here, you can see that I've created some files. So this is one of those files that you can download. And then I loaded it up here. And the way I did it is I clicked on this icon right here, which allows me to create a file. And then I just copied and pasted my code from the files that are on Blackboard, just dumped it in there. And then, you know, if you need a little touch up, I did that. And now they will run. So for instance, well, looks like I got logged off. Okay, I hope we're back. If I do demo 1, it is, oh, that's a solution to an ordinary differential equation. What it is a decaying exponential envelope with a sinusoid inside of it. And this is a script that's running. I think this is programmed so that if you hit enter, it will connect the dots with a straight line. So that gives you an idea of what the solution looks like. And if you press enter again, it will fit a smooth curve to that, which is much better. And I'll explain about that more in a minute. But, and I think at that point, yeah, it says demonstration is complete. So I'm back to just having a command here. And the other one that I have in here, and that you will have in here if you were to load the files that are available on Blackboard, is this one solves the Van der Pol equation. And so those are the dots computed by the numerical ODE solver. And what I am telling you here is that here I'm just connecting those dots with a straight line. You can't do it with the online version, but with the local version, you can zoom in on here. And if you do, you'll see that this is not really a very satisfactory solution. But this will fit a smooth curve to it. And if you zoom in there, it actually looks very good. So that's just examples so you know how to do that. Now the one, the Van der Pol equation, there's a whole lot of lines in here, but most of them, any line that starts with DISP is just displaying text. So the actual computing is extremely small. And if you just want to know how to compute, you look at demo 1, and it's got it right here. This is solving an ordinary differential equation, and it is calling the file myode.m. And if I look in here, oh, that's what it was complaining about before. I have a capital O here, and Octave, neither Octave nor MATLAB like that. They're case sensitive. So I suspect this may get rid of the error message. It does. So that's solving an ODE. I should have done this probably. Let me cancel out of here. Oh, I guess I can. Okay. I'll clear the command window, and then I will run it again. And what it's doing is it is calling this code right here, and it's sending a formula for the right-hand side of an ordinary differential equation from my ODE. That is stored here, and there's not too much to it. It's pretty simple. So it solves it, and you get t coordinates and y coordinates, and that's what's being displayed here as dots. Then it plots them. That's this command right here is what makes this picture over here with the dots. And then it pauses until you press return. And then at that point, it builds a cubic spline function, which I'm going to explain a little bit later. Right there, it builds the spline and draws the curve on top of it. So if I can get back here, that's the straight line interpolant, which is, you can see, for instance, down here, that sharp corner doesn't look much like a differentiable curve, right? But the spline will smooth that out, make it very nice. So that's the reason that I have this this folder here is I can just type a bunch of stuff in during class and say, see how nicely this works. But if you are not able to actually get a hold of the code yourself, it's a lot of writing in a real hurry to try to copy my code. So this gives you examples which you can easily modify and turn them into into scripts that will solve other equations. And all you would need to do that is back here where I have my ODE.com, it is in the instructions, it'll tell you which line, but it's right there. That's specifying the differential equation. So it's just one line to modify to get another ODE. So that's the explanation of the content in the Blackboard file. Okay, the second thing I want to mention is this. I've actually had a couple of people, 3 people so far, have mentioned to me that they were having some challenges with the current homework assignment for one reason or another. And for one person, I said, one person asked me for an extension to hand it in a little bit later, and I agreed. But since I've also had people saying that they could use some help on the homework, I think what I want to do is just to make this even-handed and offer to anyone the extension I offer to one person, which is this. If you would like to retain your homework until sometime Saturday morning and email it to me at that time, that's acceptable. So even if you're attending in class and you've already given me the paper, you're welcome to take it back and submit it a little bit later if you need to if you need to fix some of the stuff or complete a problem that you didn't have done before. So what I want to do next is answer a few questions about the homework, and then I'm going to give at least an introduction to ordinary numerical solution of ordinary differential equations. So with that, I will go to questions, and let's see here. I am watching the chat box on Zoom, as well as listening and watching the people in the room. So I know, Dustin, you had at least some problem you'd like to suggest for discussion.
Like, I think one of the toughest things was just trying to find a pattern in the recurrence relation terms once you start getting your A1, A0, A2, etc.
Okay, you had a particular one, didn't you, that came up on? Do you?
All of them.
Oh, okay. Do you want to suggest one? Let's see. I think you're previous.
Maybe number 5.
Oh, see if he wants to grab his paper. Future, you're welcome if you want to pick it up.
check and then
Yeah.
get it back to you in the.
Yeah, sure, sure. Sorry. Okay. Give me a problem, and then and for those online, I'll switch over to the document camera as soon as I got one here to comment on.
Oh,
Give me a favor.
Number 5.
Okay, and what's that say?
In parentheses, 1 plus x times y prime equals y.
Okay, so,
I copied it right anyway.
well, if not, it might be really fun. There's too many buttons on this interface. I end up hunting every time. Oh, there it is. They slid that one way over to the left. Okay. Everyone, I think now is seeing my notebook paper. So the question is, there's some issues that come up with solving this by power series method. I think it terminates. Is this the one that?
Yeah, after A1, everything I had like just turns to 0.
Yeah, okay. So let's first solve this by separation. This is, of course, dy over dx. So I'm going to divide each side by y. And then I'm going to divide each side by 1 plus x. And then I'm going to multiply each side by dx. And I think that gets it separated right there. So that tells me that the log of y is equal to the log of 1 plus x or x plus 1, whatever you wish. And the chain rule factor, of course, would be 1, so we don't have to worry about that. That tells me that, if the log of two things are equal, then the things are equal. So it looks like y equals x plus 1. Now, I should be just a little bit more careful here. I do have an additive constant there, right? And so if I'm going to fix this up, I'm taking exponential of both sides. So that tells me I've got C2 times x plus 1. So that appears to be the general solution here. And just to check that, if you took the derivative of this, you'd have C2. So you'd have C2 times x plus 1 equals C2 times x plus 1. Sure enough, it works. So that we know the solution, and that's really handy because these power series methods can get so dramatically messy as you step through them. All right, so now we're going to transition to power series. So this was sort of the cheat sheet step. We know what we're looking for. We should get a constant term, a first degree term, and then it should just end. So we are going to assume that y has this form right here. M goes from 0 to infinity, amx to the mth power. And if it turns out that after a while, all these coefficients are 0, then that would mean we had a polynomial solution. So that's actually what should happen here. And of course, that's dependent on doing everything just perfectly right all the way through, which is in general, not assured. It's easy to make little errors and then have to go back and clean them up, but we can do that. Okay, so actually when you take the derivative, normally we say start at 1 because that first term is 0 anyway, and then we're going to pull these m's down by 1, push those interior m's up by 1, m plus 1, am plus 1, x to the m. And now if I plug these series into my original ODE, which is right here, then I get this 1 plus x times the series. M goes from 0 to infinity, am x to the m. Is equal to the series for y prime, which is right over here. Sum m goes from 0 to infinity, m plus 1, am plus 1, x to the m. Okay, now this, you distribute your series across the 1 plus x. So 1 times this series is just that very series right there.
Should it be y prime on that side?
It sure should. Is that, what did I do? Put them on backwards? I sure did. Well, thank you. Scratch that. This is fixable at this point. What I'm going to say is 1 plus x times y prime is supposed to be equal to y. So another way of looking at it is 1 plus x should be over here. So here's my y prime series times 1 plus x equal to y. So that'll be okay. Now I'm going to do the expansion on this, and I'm going to subtract this from whatever's over here, and that'll be equal to 0. So sum m goes from 0 to infinity, m plus 1, am plus 1, x to the m. Then when I multiply this series by x, the power of x goes up by 1. And then I'm going to subtract this series from both sides. And that should equal 0. Okay, now let's see. This one is has x to the m, and this one has x to the m, but this one has x to the m plus 1. So I would like to lower these m's in here by 1, and or I could bump these up one way or the other. And then the starting points will not agree anymore. So what's nicer anyway? I think we're used to seeing indices, the subscripts at m plus 1, but not m minus 1. So let me just double check here. A plus 1 got dropped, didn't it? Yes. This is an am plus 1 multiplied by 1 gives this, multiplied by x gives this. That should indeed be an m plus 1. Okay, so I've done enough of these that I have intuition now, so I look at it, and if it feels wrong, I go back and check. Okay, now I would like to bring these m's down. So m goes from 0 to infinity. By the way, let me just mark this one and this one. Those are already on x to the m, and they both start at 0. So we could put them together, and that might be, that might help a little bit. So m plus 1 times am plus 1 minus am. And both of those are coefficients on x to the m. And then I've got this other thing to handle here. And what I would like is to bring all these m's down by 1. M, am, x to the m. And let's see, I brought those down, so I'll push that up. And just to double check, when m is 0, this looks like 1a1 x to the 1. And when m is 1, this looks like 1a1 x to the 1. So we have it working. And now I would like to combine this and this. Okay, now, let's see, we've got m plus 1, am plus 1, and then, just to make it particularly miserable, we have coefficients on am. One of them is minus 1 and the other one is m. So this looks to me like m minus 1. So we've got m plus m and minus 1 times am. And then all of that is the coefficient on x to the m. And that is good as long as m is at least 1. So I really should amend this here and say, no, start that at 1. And then I have the one exceptional term that comes out of this. When m equals 0, this is a special case. And sometimes we know that those will fold back into the other formula, but at this point we can't tell until we study it a little more carefully. When m is 0, I get 1a1 minus a0 multiplying x to the 0, so times 1. And all that adds up to 0. Okay, now this tells me, this special case here tells me that the 0th degree term and the 1st degree term have the same coefficient. And by the way, look all the way back here, the coefficient on x and the coefficient on the constant are the same. So we just duplicated that feature right here. The other thing that will come out now is a recurrence relation. If I solve this for am plus 1, so you set this coefficient equal to 0, and you'll get am plus 1 is equal to, okay, so I'm going to push this to the other side of the equation, minus m minus 1 am and divided by m plus 1. Now, we already know what to do for a0, of course, is a free choice. That forces a1 to be equal to our choice for a0. And now we'd like to know how to get a2. Well, for a2, you set m equal to 1. Well, if you set m equal to 1, then in here, you're going to have minus 1 minus 1. So we're plugging in 1 for m here. a1 over 1 plus 1, 2 in the denominator. Well, that's 0. Now, once you've got a 0 for a2, notice if you put m to be 2 in here, so you'd have 0 is equal to some stuff, still going to be 0, equal to a3. Once you have a3 is 0, that will force a4 to be 0, that will force a5 to be 0, etc. So, and am equals 0 for m greater than or equal to 2. Well, we've solved it. So what we know is all the coefficients are 0 with 2 exceptions. a0 and a1 must be equal, but they could be anything you like. And that's really what this says. A0 and A1 must be equal, but they could be anything you like. So this gives me, let me just save a bit of paper here. So up to the top of the page, I'll write down the final solution. For you watching online, it doesn't much matter because I got to scroll anyway. So this is what I know. A0 equals A1. So Y equals, let's give it a name, say C. And then that tells me that A0 is C and A1 is C. And that tells me that Y has to have this form, C times 1 plus X. And that is equivalent to the one I got by separation. This always happens when you have a polynomial solution. Eventually, in your recurrence relation, one of these terms will be 0, and it kills everything after that. Okay? So it does look tricky the first time you see it. But once you recognize what's going on, then you realize, oh, all right, this is the easy case. We have a case where the infinite series simply terminates at some point, and we got a polynomial for a solution. Does that help with this?
Yeah, I think I was trying to figure out a way to take some sort of pattern where everything turns into 0 and stick it back into a power series.
Oh, okay.
But so
Okay.
it seems like
Well, in a certain way, we do that. You know, this is what we're saying. If m is at least 2, then that coefficient right there is 0.
So it would be just that way you would have the little addendum like for m greater than 0, it's 0.
Yep. So
So you can do that.
so it terminates. Yeah. It's and you know, I want to be careful how I say this, because the first few times you experience some of these things, it's just not the way we're used to getting information about functions. But once you have experienced it a few times, then you probably would come to the conclusion, well, something like this, it must be possible for something like this to happen. Otherwise, I could never get a polynomial solution. And we know that there are differential equations that have polynomial solutions. So it was just a question of what it looks like when it happens. And you now have the answer. It looks like this. Eventually, all the terms turn to 0.
I think too, because for basically all of these, the whole thing that you have, like right before you have your recurrence relation there,
Mhm.
like that all those coefficients are 0, right?
Well, we know now, yes,
Right.
all but the first two will turn out to be 0.
But I mean, just generally, because like you're setting your equation. to equal
Oh,
0,
yes,
so-
yes.
But in this case, they literally are 0.
Yes. Mhm.
I think that was also just part of why I was confused.
Okay. Yeah. This is a whole different style of thinking about finding functions, right? It turns out to be incredibly useful, though. In numerical analysis, I don't know. I wrote a doctoral dissertation in an area that was pretty close to numerical analysis. And I don't think there was anything I either read or worked on myself that didn't in some way involve infinite series. They just pop up. Now, that doesn't mean everything I did was an infinite series. There was a lot of different stuff, but every major topic, it was in there somewhere. And typically it was in error analysis. So, and in other, but sometimes it comes up in other ways, and here's one of the other ways. Okay, so that kind of means most people should probably get number 5 right now. I'm assuming. It's fine to choose a different name. Yeah.
No, it wasn't consistent. So someone A0, someone C.
Oh, no, that doesn't matter. Because notice, I did both, right? Yeah, but it should be logically, mathematically equivalent to this. Okay, is there another question, Sam? Do you have something to ask about? Can you tell me what the question says? Solve this by, okay, same thing to start. Actually, I think usually we start by separating, right? So we've got dy dx equals xy, and taking, dividing by y and multiplying by dx, we have dy over y is equal to x dx. And then if we integrate, we're going to get log. It's technically the log of absolute y, but almost, I don't think there's an exception where the absolute value doesn't get absorbed in the possibility of a constant turning positive or negative later on. So it's just not worth putting it in. So integrating both sides, we get this, and then taking the exponential of both sides, we have y is equal to c2 e to the x squared over 2. Oh, and that's our old friend from, oh, not quite. It would need a negative on it to be matching the standard normal distribution. But it's similar to that, and it's something that we've worked with before. Okay, so that's what we're hoping happens, right? The more challenging part is starting from here, y prime minus xy equals 0, and duplicating that effect. Now, if you are, if you're sometimes have a little trouble recognizing the series, because for a lot of people, that is a very significant step in the process. They get the series, and then they think, what on earth am I looking at here? And someone else says, well, clearly that's the sine of 2x or something like that. And they say, well, it might be clear to you, but not so much to me. So why don't we write the series for this one ahead of time so that we know what we're looking for? So it's not required, but it's probably a good idea. We know this, e to the x is the sum, m goes from 0 to infinity, x to the m over m factorial. So we know that pattern. So if we want to replace, if we were to replace this x by x squared over 2, we should have the series for e to the x squared over 2. The constant part, we'll not worry too much about that right now. E to the x squared over 2 is the sum, m goes from 0 to infinity. All right, now I'm going to take x squared over 2 and plug it in here. Well, x squared to the m would be x to the 2m. I already had an m factorial down here, but then the over 2 to the m produces a 2 to the m in the denominator. So this is the kind of pattern we're looking for. We should have only even powers on x, a factorial and a power of 2 in the denominator. So that's what we are hoping to see. Okay, now at this point we've done the derivative enough that we probably can write this down without too much difficulty. Okay, when you take the derivative of am x to the m, you're going to have m, I'm going to leave just a bit of space there, am x to the m minus 1. But then I'm going to bump that back up to make that an m, and that will make this an m plus 1, and this an m plus 1. And I think that's what we got last time for the derivative. Fortunately, we have that stored here on our paper memory bank, and sure enough, 0 to infinity, m plus 1, am plus 1, x to the m. So, okay, minus x times y. And this time I was a little more careful. This is y prime, and that's the series for y prime. X is here, and I'm going to write the series for y. Okay, now when I put that x inside, of course, let me skip a step and say I could have done this all at once, really. I would just bump that up by 1. Okay, so we have x to the m in this series, and we have x to the m plus 1 in this series. So we have to make these things agree. Otherwise, we can't put them together as a single series. So this could go up to m plus 1, or this could come down to m. It doesn't really make too much difference. If I bring this one down, I'm going to have a subscript of m minus 1, which actually is fine. You can work with it, but we've never seen it that way before. So let me do it the other way around. I am going to bump these up. And if you did yours the other way, that's fine. It will be equivalent at the end. Okay, and let's think if I put these up, then I would have to put this down, right? Oh, and then we get something else we're not used to. So I guess all of my careful planning came to nothing anyway. Let's just double check. When m is minus 1, this produces 1 a0 x to the 0. And when x is 0 here, you get 1 a0 x to the 0. I think we're okay there. And now we have them both agreeing. So I've got an exceptional case. When m is minus 1, I get a term from this series, but not this series. So let's write the special case down. When m is minus 1, I've got 1 a0 x to the 0.
The subscript on that a be m plus 2.
M plus 2. Yes, everything went up by 1 except that. Yes, 2. So that changes this, right? When you get minus 1, that makes this a1. M minus 1, yes. 1 a1 x to the 0. Okay. All right. Now what's left over? I've got m plus 2, am plus 2 minus am x to the m plus 1 equals 0. All right. Now, this series starts with x to the 1 power. So there is only one constant term in this whole expansion, and it's this right here, a1. Therefore, a1 itself must be equal to 0. There's no alternative. Otherwise, you can't get a 0 on the left-hand side. Over here, I get a recurrence relation, but notice it skips by 2. am plus 2 is equal to, pushing that to the other side of the equation, am over m plus 2. And I should have gotten a factor of 2 in here somewhere, shouldn't I? Because I'm expecting a 2 right there. So my intuition says there should be a 2 right there. Could it have been lost somewhere, or did I do that solution wrong?
think I ended up getting it just from having that term on the bottom, like once you start adding up the m's.
Well, let's go with it for a while and see what happens. And if it's missing a factor or two, then we'll go hunting later. Now this is producing one effect. We definitely want it. At this point here, you can see that you only get even powers on x. So when A1 is 0, that's going to force A2 to be, well, it's going to be not A2, A3, A1 over 3. This number and this number agree. This number and this number agree. But that's 0. So that forces A3 to be 0, which forces A5 to be 0, etc. So all of the odd subscripted terms will be 0. That we expected. So that's looking good. Oh yeah, okay. I found it. Okay, there is a 2 in here, but it's hiding. Okay, so now A0 is free choice. A2 is equal to, apply the formula now, when m is equal to 0. A0 over 2. Then A3 is equal, not A3, I already know what that is, that's 0. A4 is the even subscripted terms that I'm trying to compute. A4 is equal to, well, you make that 4, which is to say m is 2. A2 over 4. A2 over 4. So that is, but A2 is A0 over 2. So it's A0 over 2 times 4. Yep, the 2 is in there. You're right. A6, well, this subscript and that factor agree. So we're going to have a 6 down here, and then we'll have an A4 on the top. But A4 is known. A4 is A0 over, let's say, reading from right to left, 2, 4, and now I've got a 6. And at this point, you probably have noticed that if you took a 2 out of this, this, and this, you'd have 2 cubed times 3 factorial. And this one up here, that is 2 squared over 2 times 1, which is 2 factorial. And it would appear then that A2m is equal to A0 over 2 to the m factorial, exactly as we had predicted way back here. So that's where that comes out. The tricky things that occur here is, number one, we have a recurrence relation that jumps, it skips not by 1, but by 2. And if you wrote yours in terms of m and m minus 2, that would be fine. This would say am, that'd say m minus 2 for the subscript here, and this would be an m instead of an m plus 2. But that's fine. All the same meaning. And you should get this pattern for your coefficients. Once you know that they skip by 2 from the recurrence relation, and you have the first odd subscripted term as 0, that forces all of the odd subscripted terms to be 0. And that's the other kind of tricky thing that you've only seen once before. And it happened essentially here on the last one. The recurrence relation here is skipping by 1. So once you get a single term to be 0, then all following terms are 0. Here, once you get a single odd to be 0, all following odds are 0. And it could happen with evens or whatever. Tim, does that help? Can you tell me what were you finding to be tricky on this problem? Oh, in adjusting things.
Yeah, I got to a point where I had like, when I tried to solve for AM plus one, I got AM plus one equals zero. That's because I messed up.
Oh, okay. Let me tell you, I have a trick of last resort when I work on these. Um, it is definitely the case that it's very easy to make a tiny little mistake. And having written it, most of us then become incapable of seeing it after a couple of tries. Well, of course it's correct. I computed it, right? So what I do in that case is I work on something else, or I put it away and go to bed, get up the next morning and try again. And usually I can find it. Of course, this assumes I've got another day available, but it can really help with finding some stupid arithmetic or little algebra slip up, you know, that you know better. It's just a mistake. Okay. Well, that's a couple of series, and I don't wish to solve all the series problems from the homework. Was there any other topic that we should talk about? I am watching my chat box here too, so. Okay, so same rules for everybody. If you would like to retain your homework for a little while and do some work to it, that's okay. Get it to me in the AM by Saturday. Of course, Friday night is fine, and I'll be happy to accept it. Let me okay. Let me give you a yes. Yeah, oh, I didn't see it. Problem number 7. I will discuss number 7. I don't want to solve another one in detail, but
I don't think they're fun.
can somebody tell me what? Well, I don't want to give away all the answers. Homework turns out to be kind of.
So y double prime plus 9y equals 0.
Oh, okay. This is one where, first of all, let's solve it without infinite series, okay? And I'm going to make some comments, and then Jack, you can tell me whether the comments are helpful. I may be able to guess the issue because I might have already answered that kind of question. First of all, this is a second order linear ordinary differential equation that is homogeneous, and that tells us that if we write down the characteristic polynomial and solve that, that allows us to write down the solution to this, the general solution to this homogeneous equation, which is this. Now, this is fine, and we sort of know what to expect in terms of series on this. We know that e to the 3x is equal to the sum. M goes from 0 to infinity. Well, e to the x would be x to the m over m factorial. So if you replace that x by 3x, you just pick up a 3 to the m in the numerator. And e to the minus 3x, that would look like this. It's really just the same, except every other term is going to be negative.
Hey, Professor.
Mm-hmm.
I think your lambdas are wrong. It should lead to a complex solution.
I got plus or minus 3i.
Oh, You're right. You're right. Okay, that is what I've been doing this. Oh my goodness, it's right there. Okay. Okay. I've been working on the solution for this and pretending that that was a negative, but it isn't. So you're right, Jack. Thank you. Let's try again. Lambda squared plus 9 equals 0. So lambda squared equals minus 9. Lambda equals plus or minus 3i. And maybe to emphasize, is 0 plus or minus 3i. Applying our formula, y is equal to e to the 0x times the quantity c1 cosine 3x plus c2 sine 3x. Okay, now this is a constant. So I'm getting cosine and sine, which means I'm expecting to see these kind of series here. -1 to the m. Now, if it were just plain old cosine, you'd have x to the m to the x to the 2m over 2m factorial. That would be the cosine series. And the sine series would be -1 to the m x to the 2m plus 1 over 2m plus 1 factorial. But that's not quite what we have. There's a 3 in here. So if you replace the x by 3x, you just pick up a factor of 3 to the 2m. And here you would expect a 3 to the 2m plus 1. Okay, now let's think about what the first term of this series looks like. This guy right here. The first term of the series is 1, minus 1 to the 0. 3 to the 0 is another 1. No x, just x to the 1, over 2 times 0, well, we just get a 1, right? What's the next term? Well, it's going to be negative. Then I'm going to have 3 squared over 2 factorial times x squared. And then I'm going to have a plus. So now I'm up to m is 2. 3 to the 6, x to the 6 over 2 times 3, 6 factorial. Minus, plus, forever. That's the cosine, and the sine will be something like it. Oftentimes, things get a little bit tricky for 2 reasons. Number one, this is going to be the A0, and that's going to be A2, and that's going to be A3. The other series, you're going to split, you're going to get a series that's going to split into even and odd series. The other one, that's going to start out like this. When m is 0, that's going to give me a 1 times x to the 1 times 3 over 1 factorial. So minus, plus, something or other. But the point is, you want this one to look like this: 3x minus something plus something, and so on. So when you start with A1, that will turn out to be a free choice. if you set it equal to 3, you'll get the series popping out that you're looking for. Or maybe a little bit better, set it to 3c, and then you can factor the constant c off. But the point is, you would like that one to start with a 3 showing up in it. And it's A1 will turn out to be a free choice, so you can. You just kind of put the 3 in there. Does that address the issue for you, Jack?
Still doesn't really make sense to me.
Can you give me a little help on what part of the where it gets difficult?
I guess since we went straight from the power series solution into like expanded instead of like how we normally walk through it.
Uh-huh.
I guess that's what I'm just confused how we get to, because right, like usually the answer is like y equals c like 1 plus x or something, whereas like the answer for this one is going to be y equals cosine 3x plus sine 3x. It just is weird how there's like 2 parts kind of to the solution.
Okay. Did you get to the point of getting a recurrence relation, AM plus 2 something or other?
Yeah, so I got to the part where I had the power series for y double prime and the power series of 9 times y
Uh-huh.
equal to 0.
Okay.
And yeah, I got, do you want to know what I got for the
Yeah, when you
recurrence?
solved that for AM plus 2, what did you get there?
I got -9 AM over m plus 2 times m plus 1.
That sounds correct to me. And if it helps any, you could write it this way. It's -1 times 3 squared AM over m plus 2, m plus 1. Now, here is where the step comes where it splits into 2. Notice that this jumps from m to m plus 2. So what that means is A0 is going to be a free choice. And that is, once I have A0, that's going to force A2. Once I have A2, that's going to force A4, etc. So I'm going to get the even subscripted terms here. So what that means is I am generating the coefficients for, let's see, where did I put it? I'm generating the coefficients for the cosine series right here. I've got even powers on x, and so these coefficients, if that's x to the 2m, that is a formula for a sub 2m. In the same way, A1 is going to be a free choice. The reason it's a free choice is once I choose A0, it fixes all of these, but it has no effect on A1. So A1 is free to range however you want. But once you have A1, that's going to force the value of A3. And once you have A3, that's going to force the value of A5. Do we agree up to there? Is that clear or not?
Yeah, that makes sense to me. Wasn't in the past, in one of the past, I think it was the E, when it was E raised to the x squared divided by 2, it had kind of the same pattern. It was am plus 2 equals something with am on the other side. So I guess what makes it different from this one?
What the difference is, the difference that we already saw tonight on this solution here. On this one, we got a 0 that forced a lot of zeros later. So if I were solving a differential equation that ended up being some constant times e to the x squared, or x squared over 2, you know, it wouldn't matter. What you would find is that the A1 would be forced to be 0. And it seems like we did have that. Oh yeah, it's right here. The A1 is forced to be 0, and that kills off half of the coefficients. In this case, that did not happen. So the even subscripted terms are all linked and the odds are all linked, but neither one of them drops out to 0. So let me grind through a couple of these terms over here, the A1s, and I'll show you in general how to handle that. So if A1 is free choice, then once I pick A1, that's going to force A3. So that's going to be, it's going to pick up a minus sign. I'm going to pick up 2 factors of 3. I'm going to have A1 here. And then on the bottom, notice m plus 2 is here and here. So this is going to be 3 times 2. And of course, you can get the 1 for free, right? So this one is minus 3 squared A1 over 3 factorial. Let me do one more, and I think the pattern will start to show up. Now, when I've got a 5 here, I have a 5 and a 4 in the denominator. I pick up a minus 1 from compared to what I had previously, always. And 2 factors of 3, and then I've got to have an A3. So I take the negative of this negative to make it positive. Then I've got 3 to the 4th, A1. I'm replacing this thing is going in for A3. So we lost the minus, picked up 2 more factors of 3. Then we have 5 times 4 times 3 factorial is 5 factorial. Now, at this point, it's looking like we're generating this pattern. A2m plus 1 is equal to minus 1 to the m, 3 to the 2m, A1 over 2m plus 1 factorial. If you were to chase this out, you would generate this pattern right here, which is not quite what we were hoping to see. Did I write that down? Yes, I did. What I was really hoping was to find a 3 to the 2m plus 1. Well, I can get it. What I can do is say, well, after all, A1 is a free choice. So I choose it to be 3 times a constant. So then this becomes, I'm out of room on the right, but this becomes minus 3 cubed times that constant over 3 factorial. This one becomes 3 to the 5th times the constant over 5 factorial. This one becomes minus 1 to the m, 3 to the 2m plus 1 times the constant over 2m plus 1 factorial. And so this part of the sequence, just this part, you know, these are all yet to be accounted for, the even subscripted terms. All this is generating this series, a constant, times -1 to the m, 3 to the 2m plus 1 over 2m plus 1 factorial, x to the 2m plus 1. And that is c sine 3x. Does that get us down the road a ways?
Yeah, that makes a lot more sense.
Okay, so now you have to do a similar thing for the even subscripted terms, and then you just make a note and say, oh, behold, this separates into two series. One is a cosine, the other one is the sine. And that works out fairly well in this case because we had an e to the 0x here. Had this been like an e to the whatever 5x, this thing would be a nightmare. I doubt that you'd ever, you could write down the series, but it would be really tough to translate that to exponential times a sinusoid. That would be very hard. Last comment to make on these kind of series is if this same thing happens, but you don't get the minus signs, well, then you're looking at cosh and sinh rather than sine and cosine. And don't forget that the cosh of, so this is not this problem, but similar problems. The cosh of x is equal to e to the x minus e to the minus x over 2, and the sinh is e to the x, I said it backwards, minus e to the minus x over 2. So plus and minus. So notice a linear combination, c1 cosh x plus c2 sinh x is equivalent to some other linear combination, let's say a e to the minus x plus b e to the x. So as you're working through these series problems, if you get this, say, by separation and this by series, that's just fine. They're actually equivalent. So don't be surprised if that happens. And it just kind of depends on how you handle the problem. You might have cosh and sinh for both ways of solving it. You might have e to the minus x and e to the plus x for both ways of solving it, or you might get a mixture. But just realize they are mathematically equivalent. The constants will be different, but that's all. Okay, well, that's the review of homework. And let me say, I am not particularly surprised to get a lot of questions about series. This is par for the course. So that's also why things were scheduled in such a way that we're a little bit flexible right about now in the course. So I'm going to now start talking about numerical methods for ODEs, and we'll finish it off next time. So if we have a differential equation, let's write down something tame, okay? Y double prime plus, I don't know, 2y prime. It would be nice if we could solve it by hand. Minus 8y equals 0. We don't have any difficulty in this kind of case coming up with a solution. Let's hope now I can write this down without an error. So lambda is equal to -4 or 2. And we know that the solution is this. So we can easily solve this. However, it isn't at all hard to come up with fairly tame looking differential equations that we don't know how to solve at all. So what do you do if you come across a situation like that? I'm going to show you how to set this one up, but I've chosen one that's simple just so that all the algebra and everything works nicely. First of all, we learned in the past that you can do this substitution. Let y1 be equal to y, and then you let y2 be equal to y1 prime, and then you let y2 prime be equal to whatever it's equal to when you apply this equation right here. So y1 is just plain y. So that's a y1. That's a y1 prime. And that is since y2 is y1 prime, this is a y2 prime right here. So y2 prime equals, you push those terms on the other side of the equation, 8y1 minus 2y2, because that counts as y1 prime and that counts as y1. So, which is the same as y. Okay, so I have converted my second order equation into a first order system. y1 equals y1 prime, rather, you got to read it backwards. y1 prime equals y2. And y2 prime equals 8y1 minus 2y2. And since this one is linear, it turns out that you could write it in vector form. This step right here, you cannot do if you don't have a linear equation. y1, y2, take the derivative of the vector function, is equal to a matrix 0, 1, 8 minus 2, y1, y2. So if you have a linear ODE, you can do this. If you don't, you can't. You wouldn't be able to get past here. So for example, suppose I had this system, y1 equals, now you might have this part being the same, 0y1 plus 1y2. But this one looks something like this, y2 prime, forgot my prime there, y2 prime is equal to, well, let's suppose it's 2y1 minus, how about this, y1, y2 plus 3y2 squared. Well, this is crazy nonlinear, right? It's just not, there is no way to convert this to a matrix multiplication form. So can't convert to the form y bar prime equals a y bar because the equation is nonlinear. So I just want to point out that you can always do this, whether it's linear or nonlinear. You can always convert to a system, but you cannot always convert that system to a matrix multiplication. When you can, it's very nice because you get nice, clean code. because we're gonna talk about how to solve this with MATLAB. Okay, now, if you wanted to solve this numerically, here is the general idea. Keep in mind that what we have is, at least in terms of a system, we have a first order system of equations. So for each equation, if I had a starting point, suppose I have an initial value problem. So I've got a point on the plane here. Now, if I know approximately what the derivative is, say it has that kind of slope, and I want to get another point, then I could just follow the tangent line, come up here, that point would be approximately on the curve. Then remember, I've got this sort of a thing. Y prime equals f of x and, well, rather f of y and t. So you've got a formula you can apply at any point in the plane. So this is y, this is t. So I get a new point in the plane, I reapply my formula. What kind of a formula? Well, a formula like this, for instance. This one doesn't have a t, but it could. If the right-hand side had a t to begin with, then something would have appeared over here that would explicitly involve t. So that would allow me at this point to get another derivative estimate. Let's suppose this derivative estimate looks, that kind of a slope. So then I take another step, give me another point, and then likewise, I'll apply my formula to get a derivative estimate. Maybe that turns out to be pretty much horizontal. I can take one more step, and I can just keep on going like this. And what I should be doing is tracing out points on the plane that more or less follow the solution curve, more or less. So it won't be perfect. So for instance, suppose now I'm going to draw a picture. Otherwise, I'm going to pretend unrealistically that I actually know what the solution is. And it looks like that. Okay, so let's say this is my initial point right here. And I know that point exactly. So I compute the derivative at this point. And what I'm saying is I know if t is here, that's my starting point, t0, can I estimate the value of the curve at time equals t1? Well, the answer is yeah, follow the straight line and you'll get a new point, right? Now, the point on the line and the point on the curve are different, but they're not completely unrelated. And you can see that the line and the curve follow quite close. So had I taken a step half this distance, I actually would have pretty small error here. But if I draw it with no error, you can't see what's going on. So I have to do it something like this. And now I compute the value of the derivative of the true function right here. And that probably looks like it's just a tiny bit to the left of the maximum. So it would probably be just barely positive. So you get a tangent line. It's just going up a little bit. And then when we took our next step, we'd land like here, which in this particular case is a horrible approximation, but nevertheless, it's what we would get. And then if we followed the slope of this line here, it looks like we'd be going about like that. And if this were T3, then we'd end up at this kind of point. So our computed solution is not so very close to the exact one, but you can see that if I had cut those step sizes down to be quite small, the error actually would be also pretty small. This method right here that I'm drawing, this method has a name. It's called Euler's method. It is not a practical method for solving systems numerically. What it is practical for is understanding the general idea. How do numerical systems for solving ODEs work? And the answer is they work like this. It's a stepwise method. Given one point on or near the curve, I can compute another point a little bit further down that's also on or near the curve. Now, This one, because I took big step sizes and I'm kind of exaggerating what's going on, it looks absolutely horrible, but you can imagine ways of making this better. So now suppose I have a curve that looks, I don't know, kind of sort of like that. And maybe I have a starting point like here. So that's going to be my T0. And I want to take a step, I'll take a pretty big one, T1. So I'm looking for the place where the solution curve crosses that vertical line. Now, what I could do is follow this slope. But another thing I could do would be to check the slope at T1. And that slope looks like it might even be just a tiny bit negative, right? So, and then take the average of those two, and then I'd end up with a slope that leans more like so. Might actually land pretty close in this case. And then I'd follow a line that has the average of those two slopes, and I'd land probably about there in this case, which would be pretty close to being on the curve. And then again, to take it the next step, I'd compute the slope over here and average it with this slope. So let's try not to make it look perfect in this case. Land something like here, a little bit above the line, and you could keep going like that. This averaging kind of a method is oftentimes called a predictor-corrector method. You predict a slope from where you're at, and then you predict a new point, and then you check the slope there, and you take the average, and the average slope is probably better than the guess from just one end. And you keep repeating that sort of stuff. Now, this one also has a name. It's known as Hume's method, or sometimes called modified Euler's method or something like this. Once again, not practical. You should not use this for solving an ODE because there are much, much better ways of doing it. So how do official industrial strength methods work? Well, you got a solution curve like this, and the simplest one out there, and in fact, one that's probably the most commonly used, let's say that's T0. So I got a point here. What it will do is this. First of all, it will look at this tangent line. And in this case, when you have T0 here, you know that exactly. And we're trying to get over to say T1, and I'm trying to estimate that point right there. What they do is they take like a half of a step. So they can predict this point, and they can check the slope at this point, which would probably be almost identical to the slope at that point on the curve. So then you got a slope that involved in the calculation that looks like this. Then they'll say, okay, now I got a new approximation for the slope. They'll take that approximation of the slope, start here, and predict another point that probably would be under the curve. Now I got a point above and below the curve, right? And I can compute the slope at those 2 points. Then I could use those two slopes to predict a point that is over here somewhere. Now, it probably would not be exact, but typically it's darn close. It'd be just above or just below, and you take the slope there. And now I have 4 different slopes involved at the left endpoint, at the right endpoint, and a couple of estimates in the middle. You take a weighted mean of all of these. For the standard one, it's 2 times that slope, but 2 times the slope, plus 1 times the slope, plus 1 times that slope. Divide the whole thing through by 6, and you get a grand average for the average slope over this interval. And it is incredibly good. It will land you almost perfectly on the curve as long as you have a nice curve that isn't too wacky. So that method, it's actually due, there's a whole series of these methods due to 2 mathematicians. One was named Runge, his last name was Runge. The later one It might be the other way around. Anyway, the other one was named Kutta, so they became known as the Runge-Kutta methods. There's multiple ones. This is the simplest one. This is the Runge-Kutta method of order 4. And this is a practical method. It is probably the most commonly used method for solving numerical ODEs out there. Now, there are special cases where this doesn't work well, but it does, on the whole, work fairly well. Now, I need to tell you a little bit about what we mean by order 4. And to do that, I need to talk briefly about what is known as big O notation. The way that things are expressed usually is that this distance right here from one point to the next is usually called h. And in any practical method, h is going to be, first of all, positive and quite a bit less than 1. So h is close to 0, but not really 0. Now, how close to 0? Well, for instance, a tenth, maybe, or maybe 100th or something like that. It depends on the function and the interval that you're working on, but it will be between 0 and 1 and a whole lot closer to 0 than to 1, typically. All right, now, let me just give you a particular function. Let's say f of h is equal to 5h cubed. We would call this function, we would say that this is big O of h cubed. And what we mean is that the absolute value of f of h is bounded by some constant times h to the third power. And what we're thinking about is h getting close to 0, but from the right side. It's positive, but close to 0. So what we are trying to describe in numerical analysis when we're using this big O notation for errors is we're trying to describe how much error will be committed by following these straight line estimates rather than following the true curve. Why? Because straight line estimates, that's all we got. You know, we have maybe some pretty fancy calculations to estimate the average slope, but then eventually we're going to start at the point we're at, we're going to follow a straight line with some slope, and we're going to stop after a while and say that's our next guess for the curve. Now, good error is usually big O of h to the 4th or big O of h to the 6th. Oh, or h to the, I should probably say 5th. That's typical. Now that does not mean that there aren't 6th order methods or 20th order methods. There are, but there's usually a good reason not to use them. So an order 4 or order 5 method means this, that when you're constructing this sort of thing is oftentimes called a broken line. So these are supposed to be sharp points and all straight. So you're stepping along in your method, trying to follow the solution curve. So you're computing these points. You're going to have at the end, you know, this was supposed to be following some smooth curve. So at the end, you've got your estimated value and you've got your true value. And if you could work in infinite precision, we can't, but if we could, the smaller step size we take all through this process, the closer those 2 points are going to be at the end. So the significance of order 4 or order 5 is this. Let me give you some examples. Euler's method. Its global error is big O of h to the 1. Which is why we don't use it. The Runge-Kutta method of order 4, usually just called RK4, is big O of h to the 4th. So if there were no round-off error, what we're saying is this. What if we replace h? H is replaced by h over 2. So what would happen if you cut your step size in half? That's the big question. So for Euler's method, you would start the original step size would give some constant, approximately some constant times h. The new and improved version would give some constant times h over 2, which is kh over 2. So in other words, this error for step size h and this error for step size h over 2 differ by a factor of 2. I cut the step size in 2, I cut the error in 2. That's the idea. Okay, how about Runge-Kutta 4? Suppose we start with step size h and we move to step size h over 2. Well, RK4 would say this. At first, you would expect an error that looks something like k times h to the 4th. And keep in mind, h is a relatively small number. It's between 0 and 1. So when you raise it to the 4th power, it's starting to get quite small. But then when I replace h by h over 2, and I raise that to the 4th power, well, I get kh to the 4th again, just like I had here, but that denominator, 2 to the 4th, is 16. So cutting the step size in half, having the step size cuts error approximately by a factor of 16. So I double the amount of computation I have to do, and I get 1/16 of the error that I had before. That is good. That's a big payoff. So it would seem in principle then, well, if we'd like 3,000 significant digits in our final answer, we just make really, really tiny step sizes, right? Wrong. And here's why. Every single step is not done with infinite precision. It's done with finite precision. On a 64-bit computer, you're going to have a machine epsilon of around 10 to the minus 16. So basically, every calculation has the potential, not always the reality, but the potential of losing some of those digits. Now, if you do a few thousand of them and things are going along nicely, you know, the round-off error is probably smaller than the error committed by the method that you're using. But if you pump that up to like 100 million calculations, well, not too many of them have to go wrong before the whole calculation just goes south. So it does not work to just make teeny tiny little step sizes and hope that this gives you essentially, you know, thousands of digits of accuracy. No, first of all, your computer can't even handle thousands of digits without special programming, which would then slow it down so much it'd never get done. Or the roundup error would just completely overwhelm the calculation, and at the end you'd get complete trash. So I read one research paper which actually looked at this situation about balancing step size. So you want relatively large step size to avoid huge round off error, but you want relatively small step size to avoid, this is the error that's committed by the method itself. And that some people call that truncation error, and some people call it discretization error. So I'll call it truncation error because it's so much easier to say. That's the error due to the method and round off error that's the error due to finite precision arithmetic. The Runge-Kutta method of order 4 is good enough that if you have a nice tame function like sines or cosines, a sinusoid, in a reasonable sized interval, you can usually produce a solution that is almost as accurate as possible on your computer. So in other words, if your computer can get you 16 digits, you might well have 14 or 15 of them correct. So RK4 is very good. Now, what solutions look like then in practice are this. Remember, if we were solving like a second order system, we've converted this to a pair of first order equations. So you're trying to solve for a vector function, y1, y2. And our differential equation has to do with the derivative of this thing. So you end up with a sequence of values for y1, and you have a sequence of values for y2. The y1 reflects the original y of your equation. The y2 reflects the derivative of the original y from your equation. When you work on this in MATLAB or Octave, like the tutorials you'll find online, they usually write this with a capital Y, and what will be produced by the algorithm is a matrix that has two columns. You're going to have Y values in the first one, and you'll have Y prime values in the second one. Usually, you only care about that. So the solution in the ODE is going to be in that first column. All right, there is one other issue that gets involved here, and that is, even with a good quality numerical solution, what you have essentially are some dots in the plane. Maybe they have a pattern like this in this case. Now, what you'll find when you start running Octave is, or MATLAB. Oh, I should say this. You have another option on Octave or MATLAB. MATLAB, the MathWorks is the name of the company. They offer a free trial of their software. And I think at this point, the free trial would last as long as this course does. So you could download the free trial and free trial your way to the end of this course. And there you go. So if you'd like to use the official expensive software, you know, absolutely go for it. It's free for a little while. And you might like it so much you decide to pay for it. So I wouldn't be terribly surprised. Okay, now let's suppose we come up with these dots here. Now, if you're in a practical situation in engineering or science, so you got your dots on the plane, that isn't exactly what you were after, right? You wanted a function that you could evaluate anywhere. So what if you want to know, what if the t you're interested in is here and you know there's no dot? What do? Well, I guess you could be really crude and pick the one on the left or the one on the right. That would be one option. Another possibility, this is what we used to do eons ago when I was a juvenile mathematician in early years of high school, like with something like sine tables or log tables. We didn't have calculators, remember? You'd have values. And what if you needed something in the middle? Well, you'd compute a weighted mean or use what we call linear interpolation. You're following the straight line path between these points. Now, the problem with that, of course, is that this, by the way, this sort of thing that I'm drawing right here, this is sometimes called the broken line interpolant. To interpolate means to put a line or a curve through the points. And broken line, well, you get the idea. It's, you know, it's got kinks in it, right? Now, there is, it's not just a problem with accuracy, because you could arrange your, if you knew ahead of time, I'm just gonna need it at these few points here, T1, T2, T3, you could tell MATLAB or Octave, be sure to put these T coordinates in the solution and you'll get a dot there. So that's not the whole problem. The other problem is that, you know, this might be in some kind of a software system. So first you want the solution curve, and then you need to evaluate it over and over again at many different points. So maybe, I don't know, maybe this thing is going to control the movement of a robot arm or something like that. Well, you need to know, you know, that it's happening in real time, right? So now you need to be able to know for a little short period of time how to move different parts of the machine, and those might be the solution of an ODE. And you might not know ahead of time at which points you need to solve it. So then your next problem is to come up with a reasonable quality interpolant. In other words, fit a nice smooth curve through this. The hands down best way of doing this with without getting sophisticated is this. You find a function that uses, let me make it clear what the kind of possibilities I have here. Where you have a nice smooth curve, but it not only has the possibility of increasing or decreasing, and the possibility of being concave downward or concave upward, it also has the possibility that it could have an inflection point in, you know, like right in there, in between the dots. The way you do that is you build a cubic polynomial that fits here. You have another cubic polynomial that fits here, another cubic polynomial that fits here, and then you connect them all together. Not merely do you make them their y coordinates equal, you make their first and second derivatives equal. If you do that, you get what's known as a cubic spline function. So cubic splines, now we're just talking in general here. There are cases where they don't do well, but typically if you're just looking for a smooth function that goes through some points and you want it to be simple, straightforward, you just type it in on MATLAB and boom, it's there. You can hardly do better than a cubic spline. So cubic splines are probably what you're going to want to fill in the space between the dots. If you do that, then you actually have pretty much the same thing as if you had solved the differential equation by hand. You now have a formula. It's very complicated. You know, you got to figure out which one of these pieces you're in first, and then you use that polynomial to evaluate to get your y coordinate. But nevertheless, computers are very good at that. You figure out which segment you're in, then you evaluate a third degree polynomial, and that gives you your y estimate, and that allows you to fill in the spaces between the dots. And you can do that literally millions of times very quickly. So that's sort of the big picture of how numerical ODEs are solved. Now, that's all well and good if you know how to run the software. So let me see, I think just sharing the whole screen would be good. So that's where this stuff comes in. I showed you very briefly, and we'll come back to it in detail next time, how to get the dots. So let's suppose you already had some dots. So I think ahead of class, I actually put in some x coordinates and some y coordinates. And if I wanted to plot those, the command in MATLAB is, if I got x coordinates and x and y, you could just say plot x, y. That will get you a picture. Oh, I want this. That will get you a graph like this, not very exciting, that doesn't look like it's probably the solution of a second order linear ordinary differential equation. And I just made up those x and y coordinates. You can fit a spline this way. First of all, my x's are running here from 0 to 6. So I can make a spline function that fits those x and y very easily. It's just spline xy. But I'm not going to do it quite that way, and I'll show you why in just a moment here. So I've got x's running from 0 to 6. I'm doing my fill in the dots part now. So I want this to go from 0 and something in the middle in just a moment. So start at 0, end at 6, but I'm going to use a step size. And it's got to be little enough that my eye doesn't really notice. So I'm going to compute a whole bunch of dots in here. Actually, you don't need a very small step size to fool the human eye on a screen, because the screen isn't so good either. So the length here is 6, and let's say I would like 500 dots. So index from 0 to 6, taking a step size of 6 over 500. And if I ask for the size of that, I don't want to display it all. I've got about 500 points. XX, I called it. So I've got 501 points in here. Now I'm going to say, give me the y coordinates that come from the spline function that interpolates the xy's and is evaluated at the x-axis. And now I think, do I still have my, yeah, I have that guy there, which is not very helpful. Let's draw a better graph. Hold off says don't, it means don't retain the old graph. So I want to plot x and y and mark them, let's say, with an x. Those are the data points. And then my smooth curves come from what I called XX and YY. So it's fairly easy to draw a curve that looks really good to the eye. So I have 500 closely spaced dots in here. That's the red line, and the blue X's are the points that I'm trying to interpolate. Now, how you put that all together should be evident if you download the files that are on Blackboard. It will show you exactly how to solve a differential equation, get the dots in the plane, fit a spline to it, and then draw the graph of the whole thing. Okay? And I will be happy to answer questions and explain a little bit more in detail next time. But that's it. That's how you solve ODEs numerically. All right. Thank you for hanging in there. And I'll see you all on Thursday. Don't forget, if you earlier emailed me a homework and you'd like to work on it some more, just send me a note. That'll be fine. I'll ignore the first one and wait for your second. Did you want to make any edits?
No, I actually think I did okay. It
Okay.
just took me a while to get there.
Yeah, all right.
Good.
Good.
Glad I wasn't the only one with questions.
Yeah, every once in a while,